Okay, good morning, everybody. And I'm getting ready to roll into Remote Learning 3 here, the area between two curves. So, this is an applied integral lesson. Seems to me like we've done a lot of integrating, but not for a particular purpose in quite a while. But we have been learning the major techniques. So, we're going to take a break from that and then go ahead and move into an application. And this first application is the area between two curves. Okay, so it was very nice to see a lot of you online on Thursday. And, we'll just keep doing that as people need help. Then we can meet in the Google Meets. We can also schedule our own time outside of my office hours and tutorials and math Tuesday, Thursday morning. So we're just making this up as we go, but it looks to me like we're off to a really good start, all things considered. And okay, so today what I'm going to do is go for about a half hour and then have a very clear pause and let you go and practice some problems. At that point, that was a suggestion that many people sort of feel is a good one. So we'll do it that way. I suppose you don't have to pause and you can just keep on watching if you're so inclined. But I will go for a half hour, assign some problems that you could then go and do. And then I'll go for another half hour and assign some more problems. And as a reminder, those problems are due at 8 p.m. The same day that the lesson is presented. Please just take a picture with your phone and email it to me. Or if you have other, more advanced ways of doing it, whatever you're doing seems to be working for me. Okay, so here we go with the area between two curves. And you can see that there's a blue function f and a red function g, and we're looking at a section of it from A to B. So this is an old idea. We called it like the trilogy at one point, but I'm going to go ahead and roll out an argument that will, in the end, generate an integral that captures the green area. And, maybe you see it coming, but I do want you to sort of watch carefully and be reminded of some of the fundamentals of the development of an integral and the definition of an integral. Okay, so the first thing I'm going to do then is to grab a strip, and I'm going to focus on a strip that's over here in this zone. And let's see, I'm just trying to make that strip look like I'm using like some sort of midpoint scenario. Guess it doesn't totally matter, but trying to be here in the middle of red and the middle of blue. Okay, just so that it's a decent approximation of that green area. Okay, so then we'll do the usual stuff, and we'll talk about how this is some change in x, so that's delta x. And then I'm going to talk about how this is the difference in the heights. So we're up here at f at x, and okay, so f at x is really like this entire length, but then we want to subtract from that the height up to g, and that, of course, is g at x. Okay, so, if I could throw some, fictitious numbers on here, call this like, I don't know, 7, and call this 3. And we could obviously see that 7 minus 3 is 4, and this thing would have height 4. Okay, now that's all fine and good when both f and g are above the x-axis. So it can be a bit of a mind bend to think about this scenario over here where we're looking at the same width and I'll call that delta x. Again, just trying to sort of recenter this so it looks like I'm using the midpoints of each. I don't know, trying. Okay, not that it matters, but just so that it's a good approximation. Just trying to get this area and that area to somehow match up the little extra and missing pieces. All right, so here we have delta x. And again, this is height f at x, and this is height g at x. But since g is below the x-axis, when you put in this x value, g is going to spit out a negative number. So let's go ahead and throw some values on here. And I don't know, I'm just going to go ahead and make it up. I'm going to call this height up here 7.5. And I'm going to call this height down here something like -2. So we can actually still use f at x minus g at x, even though one part of the function is above the x-axis and one part of the function is below the x-axis. Because if you subtract -2 from 7.5, so if you do 7.5 minus 2, you do get the correct height of the column of 9.5. Okay, so unlike when we were finding the area above the x-axis or below the x-axis, and we had to worry about how the integral would calculate it as a positive or a negative, when we're finding the area between the two curves, we actually don't have to worry about that. And the height of the column will be f at x minus g at x, under one caveat. And that caveat is that f at x is always above g at x over your interval. And I'll get to that as I lay things out here. Okay, so the area of a strip, which we often called the ith strip, is f at x sub I minus g of x sub I delta x. Okay, and just because I'm trying to do a good job here, I'll try to make those eyes look more clear. Okay, so then we know that the main idea of integral calculus is that in order to get the area of the green, we add together a bunch of strips. In fact, we're going to add together n mini strips, and that will be a good approximation, especially when n is big. Okay, so I think I'm now jogging your memories as to how this little trilogy works when you develop an integral. Okay, so that is a sum of n mini strips. Now, of course, we don't want n mini strips. We want infinitely many strips. And then we will introduce the idea of a limit as n approaches infinity. And my approximation then turns into the actual area. And that is then, by definition, the integral of f at x minus g at x dx, moving delta x to dx as the infinitely small change in x and our limits of integration from a to b. Okay, so now we have an area formula. Okay, so back to the caveat. This is contingent upon the one function being greater than or equal to the other function everywhere along the interval. Okay, so there we go. We're going to be using that formula that I just developed by using our old trilogy. So as I move further and further into applied integral calculus, I'm going to be saying consistently that whenever you have the need to add together infinitely many pieces, you are doing integral calculus. Now, this is a more obvious scenario where we want to add together infinitely many columns, and we've seen it before. But as I progress, we'll run into more interesting scenarios, perhaps, where we still have the need to add together infinitely many items, and that then is the clue that you need to make an integral. And that's the theme of the next series of classes, is not just the ability to take an integral, but to make an integral from some given scenario. Okay, so let me move on. And what's going to happen next is that these curves can be positioned in some inconvenient ways. And this next series of curves is going to be this exact same green area, but rotated 90 degrees. Okay, so a couple of things are problematic here. First of all, they're not officially functions, although we can find formulas for the individual sections of the red curve and the blue curve, but they do fail the vertical line test. And furthermore, you can see that it gets a little tricky, especially in this zone over here, to find a column that really does the job. Like you'd have to make a couple of columns here and then again there. And now we're adding up kind of a lot of individual packets from height d down to the function, and then from the function down to height c. But then that's only applicable from this point where I don't even know where it is over. Okay, so like I said, the areas can, get you to run into some problems. All right, so then I want to introduce the idea that you don't have to make your columns vertical. So you can see that this would be a much easier scenario if every time I ran the column this direction. Okay, so let me position this in a much better way. So something like that. Okay, so everywhere I move this horizontal column, I have a rather nice, clean scenario. And what I wish to do then is to run infinitely many horizontal columns and come up with the area of green. Okay, so now that I've laid that out, the development is exactly the same, and I'll see how I feel here as I get going, but I may skip some of the steps because we just did them and they're rather redundant. Okay, so in this case, the blue function is always to the right of the red function. So f is greater than g everywhere. So I want to make sure that when I build these lengths, I'm considering that I want to get a positive value because it is a length after all. So the length of this would be the f at y value minus the g at y value. These functions are essentially the inverses of the earlier layout, but this is a scenario where you put in a y value and say like this y value, and then the function gives you the corresponding x value for f, and the g function gives you the corresponding x value for g. Okay, so input y, output x, as is laid out in the description of the functions. Okay, so delta y this time, that's the change in the y direction, and the length of the strip is the larger value minus the smaller value, which is blue minus red everywhere from C to D. Okay, so then here we go. The area of the strip is equal to the f function evaluated at some arbitrary height. Let's remember to call it the ith strip, minus the g function evaluated at the same arbitrary height. G being smaller than f, we'll get a positive number here, multiplied by its width. Okay, so then the area of the green is the limit as n goes to infinity on the sum of some n many strips. So using sigma notation, we can show that conceptual notion on paper. Okay, well then I just did develop the integral. That is the definition of the particular integral f of y minus g of y dy from C to D, under the assumption that everywhere f is further to the right than g. Okay, so it's exactly the same argument, but it does bring up the very good observation that you can run horizontal columns just as easily as you can run vertical columns, and either the description, which is what's happening in this case, either you'd want to do that because of the description of the two curves is in the notation where y is the input and g is the output, or as you draw the two functions, you just make the observation that it would be better to run horizontal strips, and then you can go and convert your y equals function into an x equals function instead. So you can decide which one of the variables to isolate. Okay, so we'll see that as I roll through some sample problems. Okay, so these are the two formulas that we're going to be playing around with. And the next thing I'm going to do is walk you through a series of samples that will just take some of these abstract ideas and move them into a more concrete scenario. Okay, so then let's do an example. And my first example is going to be the area bounded by y equals 2x squared plus 10 and y equals 4x plus 16. Okay, so then we have a parabola that has been moved up 10. And is twice as steep as normal. And we have a line. And we can certainly graph those either by hand or on a calculator. And it's important to get a visual, one, to find out what function is on top of which one over the region that's bounded. And two, we may use the graph to observe that we have the limits of integration from a to b, and then we need to discuss, what a and b are. Okay, so I have the picture sort of prepared. So here is the picture of the two functions. And you can see that the line is above the parabola everywhere. And it's also showing us that we need to find the limits of integration. And it looks like it's from -1 to 3, but we should confirm that. Okay, and then I'll be asking you to confirm those things on the assignment yourself, not just like be reading numbers off of graphs, graphing calculators and such. So I think, in preparation for standardized tests, you could, if it was a calculator problem, then you could use your calculator feature to find the intersection point of blue and red and get the x value on both of these. Or you can use some algebraic mean. But you should be thinking about like the calculator cheats, in quotes there, or the actual algebraic process in case it was a part when you don't have the calculator. So without the calculator, that's why I was doing some of this. It gets you to find the vertex is at 0, 10, and then you have a scenario, the scales are skewed, but it's twice as steep as normal. And then you have another, you can graph a line real quick to quickly determine that this function is above that function. And okay, so then let's go for the limits of integration. So that is to say, let's go for the intersection points without just reading it from the graph, and confirm this -1 and 3. So to find where two functions intersect, you set them equal to one another. And they're both y equals, so we'll just take the 2 halves and set them equal to one another. And then looks like we're going to have a classic quadratic that we're going to need to solve. I'll minus the 4x and minus off the 6. And okay, it's easier to deal with this when you divide everything by 2, divide by 2, divide by 2, divide by 2. And somehow at this point it feels like I did something wrong. Oh yeah, because it's 16. Nice. I did do something wrong. Okay, so let's fix that. And minus 16, that's now -6 and -6. And then this factors rather nicely into x. Oh, snap. Making all sorts of mistakes. After dividing by 2, that's a 3. And anyway, it does factor nicely into x minus 3 and x plus 1. I can do math. I got there. Okay, so confirmed. -1 and 3. Those would be our limits of integration. Okay, so then what are we integrating? We are going to integrate from -1 to 3 the function, which is the upper function. I'm using parentheses here to clearly show that it's one function minus another function. And since this red function has 2 pieces, now it makes sense that I have the parentheses so that my minus sign will land on both items. You can sort of see a negative error coming your way. All right, so then I think that I can set this up and then make quick work of this. Okay, so let's see, we've got minus 2x squared, and we've got a 4x, and we've got 6 when we combine those and order them up the way I like. Okay, so now we'll use the fundamental theorem of calculus and find the area. So a couple of reverse power rules later. So let's see, we've got -2 plucking out the constant and integrating by using the reverse power rule. And then over here, pluck out the constant and reverse power rule. And over here we have a constant, 6x. And we'll evaluate that from 3 to -1. All right, clean this up a little bit right in here. And just call that 2x squared. Okay, so build some parentheses because minus signs are coming, and put in 3. So let's see, when I put in 3 here, one of these 3's kills that one, left with 2, that's 9 for negative 18, plus putting 3 here gives me 18, so those kill each other off, and putting 3 there, I get 18 again, minus. All right, taking negative 1 and putting it in there, that turns out to be a 2/3. Putting negative 1 there, that's a 2. And putting negative 1 there, I get negative 6. Okay, so doing this busy work with you on this first one. What do we got here? This is the same as 6/3. This one is the same as 18/3. So I've got 8/3 minus 18/3, which is negative 10/3, but then I'm minusing 10/3, so that's the same as adding 10/3. I'm minusing negative 10/3. And so there you go. 18 is, if I'm not mistaken, that's 54/3. Yeah. So then 64/3 altogether. Okay, so that's a pretty big problem, although certainly it's an easy integral in comparison to what we have been doing, but it does show sort of some of the big ideas of integral calculus. Okay, so recapping, you need to get a visual about with respect to the area that is bounded, and then you might need to go find the limits of integration by setting the functions equal to one another. You should be able to pull off that algebra without issue and without a calculator, but you should think through what a calculator might do for you. Then you need to set up the integral, keeping in mind that the top function is first, and you subtract from it the lower function. And then, I suppose I have to say that's busy work for us at that point. Okay, so then here comes the second example. And the second example is a little more tricky because, as you can see, that wasn't too bad. And what we're going to do is we're going to, again, find the area bounded by, okay, so let's see, we've got the same parabola, the same line, but now I'm adding on some walls. So that will be the left-hand wall, the vertical line x equals -2, and the right-hand wall, the vertical line x equals 5. Okay, so we have the parabola, we have the line, we have the wall and the wall, and you can certainly do this by hand, but I have the visual on this already prepared. So here comes that visual. And the reason that I'm working this example is, of course, because, well, we have 3 sections to consider. And that's going to make the problem basically a 3-in-1. So we're going to need to do exactly what we did before, from -1 to 3. Okay, so I suppose I can cheat and say, well, we already did that, so that's 64/3. So that's one of the 3 sections done. But then we need to come over here and come up with a new integral, and over here a new integral, and run those. Okay, so that in some other problem you would have 3 different integrals that you need to run. Having thought about the limits of integration, And in this case, you would be thinking about the limit of integration from for one integral would be from -2 to the point of intersection, already found. Then from that point of intersection to the other point of intersection, and then from this one to the right-hand edge. Okay, so this is what we know. We have 64/3 is the area in the middle, and we need to add to that this integral. Okay, so this one is from -2 to -1, but this integral is the the first function, the parabola minus the linear one. Okay, so that's 2x squared plus 10 minus the linear one. So this is an integral that we need to wrestle with. Probably should have the brackets there. Okay, and I can see how that's just going to get a little tight in there. And then the last integral from 3 to 5, and that's exactly the same. Okay, so this one I'll just go ahead and do a quick little algebra. Okay, so we've got 2x squared minus 4x, and so as not to make any more mistakes, minus 6 on that one. Okay, so they're the same integrands, they have different limits of integration. Okay, so trying to keep things nice and organized, I'm going to go with what we have is 64/3 plus, and okay, I can go ahead and take these integrals. So over here, I've got 2x cubed over 3, and this is going to be minus 2x squared. Let me just check that by distributing -4x. Yeah. And then minus 6x. And then this guy is going to be evaluated from -2 to -1. And then we've got exactly the same thing. But this one is evaluated from 3 to 5. Okay, so I really don't feel like doing the plug and chug on that one. And I think that I can certainly leave that to you to do. But what we get is our 64/3. That's the one that we sort of robbed from the earlier problem. And then we're going to add to that this one, which turns out to be 14/3. And then we're going to add this one, which turns out to be a mysteriously matching 64/3 for a grand total of 142/3. Okay, so that would just be kind of a lot of computing, and I don't need to waste our time doing that. Okay, so we've sort of come to the 30-minute mark, and I think you can go and do a couple on your own. So I'll put down a series of problems here, and that accounts for something close to half of the assignment. And you can take a break from watching and roll out these bounded areas. Okay, thank you. And here are those practice problems.